Right. So in section 3.6, we're going to talk about exponential equations. It's an equation that includes an exponential expression, but more specifically, where our variable or unknown is the exponent. Okay. That's an exponential equation. So far, we have been solving those types of problems graphically. Let y1 be one side, y2 the other side, find the intersection. But we want to learn techniques for how to solve this algebraically. In order to solve exponential equations algebraically, we have to learn about the inverse of an exponential function, which is called a logarithm. So that's what we'll do today. We're going to be practicing going back and forth between the exponential form of an equation and the logarithmic form of an equation. Okay, so that's our goal. Lots of problems like that. And then we'll talk at the end about how to use that to actually solve logarithmic equations or exponential equations. All right, in section 3.3, we calculated the doubling time of the exponential equation for Franklin Township. I guess that gives the population of Franklin Township. It started at, or we have the equation 4,785 times 1.043 to the t power equals 9,570. This is how long it would take for the population to double. And we did that graphically before by, like I said, letting y1 equal one side and y2 equal the other side and finding the intersection. Okay, now we're going to talk about how we can, like I said, solve this algebraically. Prior to solving exponential equations algebraically, we have to learn about changing back and forth between logarithmic and exponential forms. And then we have to build an understanding of how logarithms are related to exponents, okay? You will learn to read and interpret logarithms and how to compute logarithms with base 10 and other bases. Finally, you will use what you learn to change about changing forms to solve exponential equations. Pay close attention to the idea of exact versus approximate forms of solutions. We'll talk about that at the end. All right, so evaluate logarithms using basic properties of exponents. All right, so first, one basic property of exponents that we have about the equality of exponents, if we know that a to the x is equal to a to the y, so we have two exponential expressions that are equal to each other and the bases are equal, then that tells us that the exponents must be equal also. Okay, so some exponential equations can be solved using this technique. If we can take the two exponential expressions and write them with the same base, once the bases are equal, we can set the exponents equal to each other and solve for our unknown, solve for x. Okay, how can we make the bases be equal to each other? Use properties of exponents to rewrite the expression. All right, problem number 1 is a worked out example. I don't usually like the worked out examples. We'll probably skip the rest of the worked out examples that are here and just go to the U-tries, but I wanted you to see what I mean. So if we have 5 to the t power equals 125, this is an exponential expression because we're trying to solve for the exponent. What value of t in the exponent would give us 125? Now, some of you may be able to do this just without doing much work because you know the powers of 5, that's fine. But you may also recognize that 125 can be written as 5 to the 3rd power. So our left-hand side is an exponential expression with base 5, and then we are able to rewrite our right-hand side, 125, also as an exponential expression with base 5. Once our bases are equal, once our bases are equal and we have 5 to some power equals 5 to some power, we can then use the property above and set the exponents equal to each other. This means that t must be equal to 3. That's our solution. All right, now we're going to try. I was going to say only 2 examples. There's 6 of these. On one side of our equation, we're going to be given an exponential expression with a certain base. We want to identify the base and then try to write the other side of the equation using that base. All right, for example, in part A, 2 to the x power is equal to 32. The left-hand side has an exponential expression with the base 2. We want to try to write 32 as an exponential expression to base 2. Thinking about our powers of 2, 32 is equal to 2 to the 5th power. All right. So now we have 2 to the x power is equal to 2 to the 5th power. Since our bases are the same, that must mean that x is equal to 5. Our exponents are equal to. And that's it. Notice for these problems, we're basically just asking, what power do I raise 2 to get 32? I raise 2 to the 5th power to get 32, so x is 5. For part B, 4x to the 2, or 4 to the x equals 256. What power do I raise 4 to get 256? 256 is actually 4 to the 4th power. Let me make sure that's right. 4. Clear. 4 times 4 times 4 times 4. All right, yeah, 4 to the 4th power. Okay. So now since we have 4 to the x equals 4 to the 4, we know x has to be equal to 4. We use the same kind of technique for the rest of these, but also some of our other properties of exponents that we learned back in section, or chapter 2. All right, for part C. We have 7 to the x power equals 1 over 7. Now, 1 over 7, we know that when we have negative exponents, that flips our base. So using that idea, we can say that 1 over 7 is equivalent to 7 to the negative 1st power. Then this gives us 7 to the x power equals 7 to the negative 1st power. Our bases are the same. So when we solve this, we get x is equal to 1. All right. Same kind of technique for part D, but we have to put actually our two ideas together for part D. We have 5 to the x equals 1 over 25. How can we write 1 over 125? I'm sorry. How can we write 1 over 125 as 5 to some power? We know that 125 is 5 to the 3rd power, so we can say that this is 5 over x equals 1 over 5 to the 3rd power. And then to get that 5 to the 3rd out of the denominator, we can move it up to the numerator and make the exponent negative. So we get 5 to the x power equals 5 to the negative 3rd power. Oh, then there's one more step. Then x is equal to negative 3. All right, 2 more of these. E to the x equals e to the 2x plus 1. This is 2 exponential expressions with a base of e. Our bases are already the same. If we set our exponents equal to each other, we get x is equal to 2x plus 1. And then this is a linear equation that we can solve. We can subtract the 2x from both sides. That gives us negative x equals 1, and then divide by 1 to get x equals negative 1. We'll go on to part F. 3 to the x power is equal to 1/9. Remember, we're thinking about powers of 3 here. So we'd have 3 to the x power is equal to 1 over 9 is 3 squared. Not 3 times 3, I'm sorry, it is 3 times 3, but that's 3 squared when we think about the exponent. And then to move this, the term on the right up to the numerator, we make the exponent negative. 3 to the x equals 3 to the negative 2nd power. So x is equal to negative 2. All right, so these are exponential expressions that are actually set up very nice for us. The left-hand side and the right-hand side work out perfectly so that they can both be written as the same base. In real life, however, that does not happen very often. Even if we take any of these problems, let's go back up to the first one of the easiest ones. If I change this problem just a little bit, I won't be able to solve it using this method. And let's say instead I have 2 to the x power is equal to 30 instead of 32. What power can I raise 2 to get 30? Well, we know 2 to the 1st power is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, and then 2 to the 5th is 32. But what about 30? We skipped 30. Exactly. Our answer is going to end up being some decimal We don't know that off the top of our head. We can kind of narrow it down. We see here that 2 to the 4th power is 16 and 2 to the 5th power is 32. So the decimal should be somewhere between the 4th power and the 5th power, or 4 point something, but we don't know exactly what. In order to solve this and to get an exact answer, we need another technique. And that's where logarithms come in. Logarithms give us a way to solve for the exponent in exponential expressions. Okay, so we're going to practice writing out logarithmic form. When we're in logarithmic form, just like exponential expressions have a base, our logarithms have a base. And we're going to talk about how to go back and forth between the two different forms. All right, so logarithmic functions. Logarithmic functions are used to model applications such as investment growth, sound travel, earthquake magnitude measurements. And basically, we use logarithms when we're trying to solve for the exponent, okay? We can use logarithms to solve exponential equations with unlike bases. When we evaluate a logarithm, the result is an exponent. So the answer that we get when we solve a logarithm is the exponent that we would need to get the solution to our exponential equation. So logarithms are equal to the exponents in exponential form. All right, so we start off with an example here of what the exponential form and what the logarithmic form would be equal to. If we have the exponential equation 2 to the y power equals 7, the logarithm answers the question, what power would I raise 2 to get 7? Okay, but what does a logarithmic form look like? So we're going to use the word log to denote a logarithm, and then the log has a base, like I said. We write the base as a little subscript next to the log. In this case, since the exponential expression has a base of 2, the logarithm also has a base of 2. Okay? So if we have an exponential form with 2 to some power, the logarithm has base 2. Then we have to take the logarithm of some number. The number that we take the logarithm of, which is the 7, tells us what we want our output to be. We want to end up with 7. And then what is the logarithm equal to? The logarithm is going to be equal to whatever the exponent is that gives us this output. Okay. So when we read this expression, oh, it's written up here. This is read log base 2 of x. Equals y. Sorry, I forgot that very important part. So when we read logarithms, we say log base, whatever the base of our exponent is, of whatever number we want to equal, whatever number we want to get, and we say that that is equal to whatever the exponent should be. So the logarithm tells us what our exponent should be. Again, I highlighted these 3 parts because we're going to practice going back and forth between these 2 forms. Every single exponential equation has a logarithmic form, and every single logarithmic equation has an exponential form. We go back and forth by moving these 3 parts around. Notice where the bases go, where the exponents are, and then where the other number, or what our exponential equation equals, where that goes as well. All right. So reading and interpreting logarithms. In general, if we have log base b of x equals y, this base tells us what the base of our exponential expression is. So this is saying I want to take b and raise it to some power, and I want to get, try to use my same colors, I want to get x. And the question is, well, what power do I raise it to? What power do I raise b to get x? That's y. Okay. So this is log base b of x equals y. That means b to the y power equals x. So when we start off with the logarithm, whatever the base of the log is the same as the base for our exponential function. What the logarithm is equal to, that's what the exponent should be in exponential form. And then the other number is what our exponential form is equal to. So I'm going to do a quick example of this using actual numbers. Let's say we have, and I'll use something that'll make sense to you. Let's use log base, we've seen this one a couple times, 5 of 125 equals, I know this one is going to be equal to 3. Okay, this is log base 5 of 125 equals 3. In exponential form, we're saying the base here, 5 raised to the third power equals this number, 125. So the base is the same. Whatever the logarithm equals, that's what your exponent should be. And then we'll set the exponential expression equal to 125, where we're taking the logarithm up. Number 3 is a worked example. We're going to jump straight to the practice problems. And I'm going to write up here again the relationship between the two. We have log base b of x equals y. That means b to the y power equals x. So pay attention to where the b, the x, and the y are. Those are the terms that we're going to be moving around. All right, first 4 problems here start off with logarithmic form. Start off with the exponential form, and we have to write this in logarithmic form. First thing that you want to do, you're always going to write the word log. That tells us that we're taking the logarithm. And then you want to identify the base. The base of this exponential term is 3. So the base of your logarithm is going to be 3. You want to write your base as a subscript. So that's a small 3 at the bottom of the log next to it. Okay. Then we have to take the log of something. So when you have a log, you have a base. This is saying, I want to take 3 and raise it to a power, and I want to get some number. What number do you want to get? Well, sorry, my color coordinating is hard today. We see that we want this to be equal to 81. That's what we're taking the logarithm of. Log base 3 of 81. Note, a lot of students will look at this and they say log of 3 to the 81 power. That is not correct. That's not what we're saying here. We're not raising 3 to the 81st power. We're saying we have log base 3 of 81. That means I want to have an exponential expression with base 3, and I want my output to be, or my answer to be 81. And then this should be equal to whatever the exponent is. Our exponent here is 4. So this is going to be equal to 4. That's the logarithmic form. 3 to the 4th power equals 81 is equivalent to log base 3 of 81 equals 4. Using the same technique, we're going to do parts B, C, and E. Okay. In part B, we have 5 squared equals 25. So our base is 5. We have log base 5. Our answer in exponential form is 25. So of 25, and this should be equal to the exponent, which was 2. Log base 5 of 25 equals 2. Next one. 7 to the negative 1st power equals 1/7. That's log base 7 of, and sometimes you'll see this in parentheses. I usually write mine in parentheses. You can put the parentheses or not, it doesn't matter. Of 1/7 equals the exponent, which is -1. Biggest thing to remember here is whatever the exponent equals, that's what the logarithm equals. The exponent was -1, the logarithm is equal to -1. Last one here with logarithms. The exponent is 1/2. Even before I write anything, I can say the logarithm is going to be equal to 1/2. Because in logarithmic form, the logarithm always equals the exponent. All right, but on the other side, this is 36 to the 1/2 power equals 6. So our base is 36. And we're taking the log of 6. Move that over a little bit. So we get log base 36 of 6 equals 1/2. Then next, we go the other way. So when we go from logarithmic form to exponential form, this one's a little bit easier to check. One, the exponential form that you get should be a true equation. It should be true. The first thing, look at the logarithm, whatever the base is, that little subscript, that's going to be the base for your exponential form. So we're going to have 4 to some power. What's the power? Whatever the logarithm equals. This logarithm equals 2, so I get 4 squared. And then what's 4 squared? 16. So 4 squared equals 16 would be the exponential form of this logarithm. For part F, log base 2 of 64 equals 6. That's equivalent to 2 to the 6th power equals 64. All right. If you accidentally wrote this wrong, if you wrote 2 to the 64th power equals 6, you should automatically know that something's wrong, because is 2 to the 64th power 6? No, it's much, 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 much bigger. So if you get an exponential equation that is not true, that means you wrote something incorrectly. For part G, log base 2 of 1/8 equals -3. This is 2 to the -3rd power equals 1/8. H, log base 3 of 1/9 equals -2. That's 3 to the -2nd power equals 1/9. And the last one, I, log base 5 of 5 equals 1. This is telling us that 5 to the 1st power equals 5. The common log and a natural log, they have special notations and special names. So if you have log base 10 of x, this is the common log. And instead of writing the base 10, we just write it as log of x. So this is the proper notation, just log of x. Do not write the base 10. And actually, if you look on your calculator, you'll actually see a log button. It's usually next to like the 7 and the 4 on that side, on the left-hand side of your calculator. You'll see 2 buttons. One says log, that's log base 10. And then you'll see one that says ln, that's the natural log, which is log base e. So log base e of x, we never, ever, ever write it this way, is log base e. The proper notation is ln x. So when we see ln, we should know that we're dealing with a base of e. And when we see log, no base written, we should know that we're dealing with a base of 10. Again, these pop up a lot in practice, common logs, because our decimal system is in base 10. And then E actually pops up a lot in nature somehow. So like when things are growing continuously, like we saw with continuous compound interest, the number E pops out. So ln is called the natural log because of that. It pops up often. So often that they have their own buttons on the calculator and their own names. All right, so just like we can go back and forth between log and exponential form for base 2 or base 5 or base, what else do we do? 6 and base 3, base 1/2. We can go back between logarithmic and exponential form for log of x and ln of x. It looks a little bit different though because of the different notations, so we'll practice doing that in the next example. All right, so for parts A, B, and C here, we're dealing with exponential expressions that have a base of 10. When our base is 10, the logarithmic form is the common log, which is just log. We don't have to write the base of 10. So when we write this in exponential form, 10 to the 4th power equals 10,000. This would be log, which means log base 10, of 10,000 equals 4. It's almost exactly the same as what we did before, except we don't write the extra little 10 down here. That's it. That's the only difference. For part B, 10 to the -2nd power equals 0.01. Remember still, the logarithm is going to be equal to the exponent, so this is going to equal -2. And then for log base 10, we just use the word log, don't write the base. and that'll be of 0.01. So log of 0.01 equals -2. Same thing for C. 10 to the 0 power equals 1. So this logarithm is, going to be equal to 0. And then we have log base 10, but we don't have to write the base, of 1 equals 0. All right. Now, the next example has a base of e. E to the negative first power equals 1 over e. Remember, when our base is e, we don't write log base e, we use the notation ln. So this would be ln, which is log base e, of this number of 1 over e, sorry, there's not an e, equals whatever the exponent was, -1. All right, and I was about to say, did they just give us 1? So that's the first 5, going from exponential form to logarithmic form. Going the other way, we just have to recognize that when we see log with no base written, we know our base is 10. When we see ln, we know our base is e. So for parts E and for part F, both of those have a log, so we know the base is 10. This is going to be 10 to the -3rd power equals 0.001. And then for log of 1 equals 0, we just did that one. That would be 10 to the 0 power, whatever the logarithm equals, that's our exponent, equals 1. And both of these are true expressions or true equations. All right. All right, next, for part G and F, both of these are logarithmic functions with ln, so that's base E. ln is base E, okay? So the ln part, let me just highlight this. This part just tells us that we're gonna have E raised to some power, that's our base. Whatever the logarithm equals, that's what the exponent should be. So for part G, ln of E equals 1, that's E to the 1st power, equals whatever we're taking the log of, E, which is true. For H, ln of 1 over E equals -1, that's E to the -1st power equals 1 over E. All right. So we've practiced going back and forth between log and exponential form with several different bases. We've also looked at our 2 special bases, base 10 and base E, the natural log and the common log. Now, we're going to talk about how we can use exponential form to evaluate logarithms. There are properties of logs, just like there are a bunch of properties of exponents. We're going to learn a few of them between this section and the next section, really. But in this example, we're going to practice evaluating logarithms. So let me go back actually a step. What's evaluating logarithms? So far, we've seen logarithmic equations that have already been evaluated for us, but sometimes they aren't. Like I can give you a logarithm that's something like log base 9 of 81. And I want you to tell me what this is equal to. So you have to think about what the logarithm means. This is asking, what power do I raise 9 to get 81? So we can say this is equal to, we don't know, some unknown. Then if we write it in exponential form, this would be 9 to the x power equals 81. You can solve this. Okay? We solve problems like this in the beginning. Alternatively, we can start from log base 9 of 81, and we can say to ourselves, oh, I want that, I want to rewrite 81 as 9 to some power. Well, we know that 81 is 9 squared, so this is log base 9 of 9 squared. then this kind of gives us our answer. What power do I raise 9 to get 9 squared? It's right there, it's squared. So this would have to be equal to 2. So it's basically using what we know about exponents to rewrite these logarithmic expressions and evaluate them. All right, problem 7 is worked out for us. So we're gonna jump to we're gonna jump to problem 8, which is the you try ones. Time is it 10:52? All right, we have plenty of time. I think we stop at problem 13. We go through more than I thought. All right, let's pick it up. Got to make sure we finish this today. For number 64, log base 2 of 64. You might be able to do some of these mentally if you know a lot of powers. This is asking 2 to what power equals 64? We know that to the 4th power is 16, to the 5th power is 32, 2 to the 6th power is 64. So that tells us that log base 2 of 64 must be equal to 6. So just using what we know about powers of 2. All right. For log base 3 of 1, I like to rewrite these in exponential form. This is asking, if I take 3, what power do I have to raise it to get 1? We get 1 when we raise our base to the 0 power. Okay, so since 3 to the 0 power equals 1, that tells us that log base 3 of 1 equals 0. Our logarithm equals the exponent that we're trying to solve for. All right, let's knock out the rest of these. Can't fit them all on one page, but that's okay. Oh, this is an interesting one. Part C, this is log of 1 over 1,000. Remember, log, there's no extra base written there, so we know that's base 10. This is asking 10 to what power equals 1 over 1,000? Then we can use our properties of exponents to try to rewrite this. 1,000 is equivalent to 10 to the 3rd power. So then 1 over 1,000 can be written, 1 over 1,000 can be written as 10 to the negative 3rd power. So we see here that 10 to the negative 3rd power is equal to 1 over 1,000. So that tells us that our exponent has to be -3 and that log of 1 over 1,000 equals -3. Any questions about this so far? Let me pause. We'll pause for questions in a while. I don't see anything in the chat. Hopefully you guys are following along. You know, sometimes people get a little stuck with log and ln because the base isn't written there, but just keep drilling it into your head. Log is base 10, ln is base e. All right, for part D, again, this is a base 10 problem. So log of 0 equals what? This is 10 to what power equals 0? Now that's interesting. Let's think about that. What power can I raise 10 to get 0? So we know 10 to the 1st power is 10. What's 10 to the 0 power? Not 0, it's 1. If we keep going higher, we get bigger numbers, so that won't work. What if we look at negative exponents? 10 to the negative 1st power is 1 over 10, so 0.1. 10 to the negative 2nd power is 1 over 100, 0.01. If we keep doing more and more negative exponents, into the negative 3rd power is 1 over 1,000, 0.001. If we have a 0 exponent, we get 1. If our exponents get bigger, we get bigger numbers. If our exponents get negative, we just get really small numbers, but they never actually equal 0. Remember, exponential functions like 10 to the x can't equal 0. We have a horizontal asymptote at the x-axis. So this actually has no solution. It's not possible like this. Does not exist because it's not possible for 10 to be raised to a power and we can get 0. So we'll say that this is D and E does not exist. All right, 4 more to go. Log base 10 or log of 10. This is 10 to what power equals 10? I'm going to write this over here so we have more space. We know that 10 to the first power is equal to 10. So that means that log of 10 should be equal to 1. All right, for ln of e to the 5th equals what? So ln tells us we're raising e to some power, and we want it to equal e to the 5th. Well, this one's solved for us. In order for us to get a 5 for the exponent, we have to make the exponent 5. So ln of e to the 5 is 5. This one's nice. If you have ln of e to some power, the answer is always going to be that power. Next one, ln of 1. ln is base e, so e to what power equals 1? Anything to the 0 power is equal to 1. So every time we have a log of 1, the answer is always going to be equal to 0. We know e to the 0 power equals 1, so this logarithm must equal 0. And last one, oh, this one's fun. I'm going to rewrite this a little bit before we solve it. This is log base 8 of, the square root of 8 is 8 to the 1/2 power. So when we rewrite this, we're asking 8 to what power equals 8 to the 1/2 power? We get that 1/2 back. Anytime our base here is the same as the base here, the answer always ends up being just whatever the exponent is. All right. So we practice solving logarithmic equations. Number 9 is just another example like this. It's an immediate example. So that means there's a video for it. I am going to, hold on, someone's coming in from the waiting room. Leave this one for you to practice. You can watch the video solutions for it. It's just like the problem that we did previously. And then I want us to jump into problem 10 where we're practicing evaluating logarithms. It's the same thing again, just not in the table. And there are a bunch of these. That's why I wanted to jump to this problem. These can be done. All of these are actually really nice ones by rewriting in exponential form and considering or using what we know about powers of x. So for all of these, I'm going to say they're equal to x equals x equals x equals x equals x equals x, because we're trying to figure out what it equals. That's our unknown. And then we're going to rewrite these in exponential form and solve like we did in the beginning of the class. All right, for log base 5 of 25 equals x. This is 5 to the x power equals 25. We know that 5 squared is 25, but we can write it as 25 is 5 squared, then x equals 2. So what does that mean? Log base 5 of 25 equals 2. Or you can just leave it as the x equals 2 as your answer. For part B, log base 9 of 9. That's 9 to what power equals 9? We know 9 to the first power equals 9. So log base 9 of 9 equals 1. For part C, log base 3 of 27 equals x. This would be 3 to the x power equals 27. 27 is 3 cubed. So that tells us x equals 3, or that this logarithm is equal to 3. All right, then on to part D, log base 6 of 36. I'm going to pause here really quickly. For some of you, you might not need to write this in exponential form to solve it. If you don't need to, that's fine. If you think about, or if you're comfortable with like knowing what exactly, or how to read this logarithm and what it means, they're actually not too bad, these. This is asking log base 6 of 36, what power would I raise 6 to get 36? 6 squared is equal to 36. So this logarithm equals 2. All right. Similar with E. What power would I raise 8 to get 64? Log base 8 of 64. 8 squared is 64. So log base 8 of 64 equals 2. All right, part F, log base 4 of 64. What power do I raise 4 to get 64? 64 is 4 to the third power. So log base 4 of 64, equals 3. All right, 6 more of these, and then we get to my favorite part, which is the point. We're learning about these logarithms so that we can solve exponential equations. We're going to get to that in just a second. All right, log of 1. This is 10 to what power equals 1? That has to be the 0 power, so log of 1 is 0. Ln of e to the third. This is e to what power equals e to the third? Well, that's just going to be 3. Because if our bases are both e, then the exponents have to be both 3. For part I, 10, because this is log of 0.01, 10 to what power equals 0.01? 0.01 is, what's that? 10 to the negative second power. That's 10 to the negative second power. So 10 to the x equals 10 to the negative second. This is equal to, oops, not 2, negative 2. All right, last 3, we have some fractions and different bases involved. Ln of e to the negative 7th, pay attention to h and j. Both of these are written similarly. We get e to the x equals e to the negative 7, and our answer ends up being the exponent on the e, negative 7. Right, last 2, log base 2 of 1/4. 2 to what power equals 1/4? 1/4 is 2 to the negative second power. So we have log base 2 of 1/4 is negative 2. And similarly, log base 7 of 1/49. This is 7 to what power equals 1/49? 1/49 is 7 to the negative second power. So this would be equal to negative 2. All right, now that we've done lots of practice with going back and forth between log form and exponential form and solving logarithmic and exponential equations, how can we use logarithms to evaluate functions? We need to know how to find logs in our calculator. Oh yeah, we can do problem 12. This is an easy one. You literally just type it into your calculator. Let me open up my TI-84 and we'll do all of these. All right, so going to our regular screen, let me just clear all of this out. Log is right next to the 7 button and ln is right next to e. Right now we're gonna practice evaluating with our calculator some logarithms. Literally just type it in. So the first one is log of 14. Log, when you type it in, a parentheses will open up. We'll just type 14. You can close the parentheses and then hit enter. You'll get a decimal. We're asked to round our answers 3 decimal places. So log of 14 equals 1.146. What does this mean? This means that if I take 10 and raise it to the 1.146 power, I get 14. All right, next one, log of 2/3. That's log of 2 divided by 3. We hit enter, we get negative 0.176. Oh, that was actually C. I did these out of order. That's okay though. Next, we have 2 natural logs. The ln button is next to the 4. So we'll press ln of 7/8. And enter. That gives us negative 0.134. And last one, ln of 86. ln of 86 is 4.454. All right, now that we know where to find these things in the calculator, I'm going to stop sharing here and go back to our workbook and look at how we can use calculating these types of logarithms to solve exponential equations. So this is my favorite part. Dun, 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 the grand finale. So right now we're going to practice solving exponential equations with base 10. We're going to do that by using a logarithm of base 10, the common log. First, we're going to do these 3 steps. We're going to estimate what our answer should be using what we know about powers of 10. Then we're going to solve graphically, and then we're going to use our calculator to convert this exponential equation to logarithmic form and solve for x. All right, first estimating. For 10 to the x power equals 63. Let's think about what we know about the powers of 10. We know 10 to the first power is equal to 10, and we know 10 squared is equal to, what's 10 squared? 100. So 63 is somewhere between 10 and 100. That means that my value of x has to be somewhere between these exponents. So based on what we see here, we get that 1 is less than x, which is less than 2. X is some number between 1 and 2. An exponent of 1 gives us a number that's too small. An exponent of 2 gives us a number that's too big. So our answer is a decimal between 1 and 2. For part 2, if we wanted to solve this graphically, let's go to Desmos. Let y1 be 10 to the x power. Let y2 equals 63. There we go. It's a better window. Then this intersection point occurs at 1.799. That's our answer. That's what the exponent should be. Okay, so by solving graphically, I'll do a rough sketch here really quickly. We had an exponential function here, our horizontal line here, and the intersection was at 1.799 comma 63. So we get x is equal to 1.799. All right, now the fun part. How can we solve this without having to graph? We can use logarithms. If we convert 10 to the x power equals 63 to logarithmic form, this will be log base 10, so we don't have to write the base, of 64 equals x. So all we have to do is compute log of, I'm sorry, why did I change mine from a 63 to a 64? 63. This would be log of 63 equals x. So all we have to do is go to our calculators, type in log of 63. I'm going to do that now. Log of 63 equals, would you look at that? If we round 3 decimal places, yes, we're asked to round 3, we get 1.799. And does that match up with our estimate? Yes, we were expecting a number between 1 and 2. This answer is between 1 and 2. So part 3 is really the new thing that we're learning here. How can we solve this using logarithms? Convert to logarithmic form and then put it into your calculator. All right, so for part B here, 10 to the x power equals, skipped one, 0.73. We're just going to skip to step 3. If we convert 10 to the x power equals 0.73 to logarithmic form, that's log of 0.73 equals x. Then we can type this into our calculators. Log of 0.73 is negative 0.137. And then remember what this means. You can check your answer. This is telling us that 10 to the negative 1.37 power should be equal to 0.73. You can also solve that graphically and estimate your answer too. On your lab, you'll have a problem where you have to do all 3 of these steps. All right, but Last one, before we stop for our quiz, 10 to the x power equals 1,940. If we convert this to logarithmic form, we get log of 1,940 equals x. And using our calculators, log of 1,940 is 3.288. So that's our solution. Now we can see that having these logarithms and this log button on our calculator makes it really easy to solve these exponential equations without having to graph and find the intersection.